I'm Aditi Gupta. So today we're gonna start our topic, that is hybridization. So what is hybridization? From where hybridization comes from? This word comes from hybrid, hybrid. So hybrid, as is seen in agriculture, hybrid is a variety which is formed by two different two different species, or a for a combination of two different species. So hybrid has all the features of these two species from which it is forming. So similarly in chemistry, hybrid word has same meaning. So here we use hybrid word for orbitals in case of orbitals. So if we have two orbitals, that is s s orbital, that is spherical in shape, and p orbital having dumbbell shape. So, as we know that s orbital is spherical in shape like a sphere, and p orbital is dumbbell shape, and has in s orbital the electron density is distributed in whole of the sphere, and similar electron density is present in whole of the sphere. But in case of p orbital, the electron density has directional behavior. The electron density towards the lobes are more in comparison towards the center. So p orbital and s orbital have different shapes, and due to different shape they have different electron density and thus having different energy. So what is hybridization? Now they have different energies and shape. Now in order to form a hybrid orbital, these two orbitals, that is s and p, undergo overlapping like this. So in order to overlap these orbitals, we these undergo overlapping from the same side, from a similar side, that is from plus side or from minus side. So this is our plus sign here, it undergoes overlapping like this. After overlapping, it results in the formation of orbital having equivalent energy and shape. Now this orbital, which is formed by overlapping of these two orbitals, have equivalent energy and shape. So what is meant by equivalent energy and shape? That means the electron density is similar in whole of the structure. Now the side from which overlapping takes place between two different orbitals, that lobes got bigger in size, and whereas those where from which there is no overlapping, that is from negative lobe got small in size. So we can say that the electron density is now rich in these plus lobe side in comparison to minus lobe side. So it has rich or thick electron density. So as we can see that these two orbitals now have different same shape and as well as energy, because they have electron density distributed is similar in whole of the orbital. So So now why we are doing hybridization? What is the need of hybridization? We are doing hybridization because as these two orbitals undergo overlapping, they form a orbital that has equivalent energy and shape. They have same energy and shape. Earlier they have different energies, and due to this different energy, if they form bond with any other orbital, that bond is weak in comparison to the bond formed by the hybrid orbital with any other orbital. So that is why we are doing hybridization. The bond formed by hybrid orbital is strong in comparison to simple atomic orbital. These are simple S and P are simple atomic orbital. This is a hybrid orbital. So that is why we are doing hybridization. So now let us take an example of hybridization. Let us take an example, that is BeCl2. Here we have two metals, that is beryllium and chlorine. Chlorine is non-metal, beryllium is a metal. So beryllium here is acting as central metal because those metals which has less electronegativity are acting as central metal. So beryllium has atomic number of 4 and chlorine has atomic number 17. So electronic configuration of beryllium we can write 1s2, 2s2. Chlorine has electronic configuration 1s2, 2s2, 2p6, 3s2, 3p5. So now since as we have seen ki beryllium can act as central metal atom because of its less electronegativity. So beryllium we can draw for beryllium. Since beryllium has outermost orbital, that is 2s. Outermost means which is present out to the outer side from the nucleus, or so that is why 2s is our outermost orbital. So the electrons present in 2s are outermost electrons, so that are also known as valence electrons. So beryllium, that is ground state electronic configuration or orbital diagram for beryllium is 2s having 2 electrons. Now beryllium also has a empty 2p orbital. So now in order to form bond with these two chlorine atoms, beryllium should have two unpaired electrons to in order to form bond with chlorine atom. So in order to form bond, this electron from 2s should be excited to 2p orbital. Now this electron is excited to outermost orbital 2p, that is now is excited state of beryllium. Ground state means that is beryllium is in its neutral state or its natural state, that is ground state, or its comfortable state. Now excited state is in which the electrons are free or in can easily react. Now beryllium is in excited state means highly reactive state, that is unstable state, also known as unstable state. So now it can react with chlorine to form bonds. Now as we know that chlorine has outermost electrons, that is 3s2 and 3p5. These are the outermost orbital 3s and 3p. So the electrons present in it are outermost electrons. So we can show for chlorine 3s2 and 1, 2, 3, 4 and 5. 3s2, 3p5. So in chlorine we can see that only one unpaired electron is present. So in order to complete its octet, it needs only one electron to complete its octet. So it can take that one electron from beryllium. So it can form bonds with this electron with beryllium. So now we have seen that we need two electrons to form bond with chlorine. So now these two orbitals undergo hybridization first. Why are we doing hybridization here? Similarly, as we have told earlier that in order to form strong bond between beryllium and chlorine, these two orbitals have to undergo hybridization. So that is why we are doing or showing hybridization here. So these two orbitals undergo sp hybridization. S and p, that is sp hybridization or sp hybridized. Now these two orbitals have same energy and shape. Now these, we are talking about two chlorine atom. We have two chlorine atom. Here we have written only electronic configuration of one chlorine atom. We can similarly write electronic configuration of second chlorine atom. So it has also one unpaired electron. So these two unpaired electron will form bond with these two orbitals of beryllium, that is sigma bond, because one electron is coming from beryllium and one electron is coming from chlorine. So that is why it is a sigma bond having sp hybridization. So now we have hybridization sp. So we can say that for sp hybridization, as we have seen earlier, for sp hybridization, that is orbital diagram is this, that is for beryllium. Now chlorine is using its p orbital. So for p orbital, we can draw p orbital that is dumbbell shape like this. Similar for another chlorine atom. This is for one chlorine atom p orbital, another chlorine atom p orbital which is overlapping with beryllium sp hybrid orbital. This is sp hybrid orbital, this is p orbital of chlorine, that is we can say pz orbital along z axis. So this is our z axis of chlorine, pz orbital of chlorine, which are undergoing overlapping with the sp hybrid orbital forming sigma bonds. So this is sp hybridization having bond angle of 180 degree. We can say, we can show these sigma bonds like this now, and these have bond angle of 180 degree. Sp hybridization and bond angle is 180 degree, and shape is, or geometry, you can say geometry is linear. So that's all for today. Thank you.